Donc, je vais commencer par introduire le professeur que nous accueillons aujourd'hui, professeur Bang Liu de l'Université de Montréal, membre, je pense, des deux laboratoires Raleigh et Mila, spécialisé en traitement automatique du langage naturel. Et donc, il a obtenu ses 2 diplômes de maîtrise et de doctorat de l'Université de l'Alberta à Edmonton. Donc, professeur Liu va nous parler aujourd'hui de la compréhension du langage naturel, Data, Knowledge and Logic, Modeling and Reasoning for Natural Language Understanding. Donc, you can start, Professor. Thank you.
Okay. Thank you, Professor Fatia, for introduction and the invitation. And thanks everyone for attending my talk. So I will start sharing my screen. Today I will talk about data, knowledge, and logic, modeling and reasoning for natural language understanding. So basically, I will introduce a part of my research works. So this is the outline of today's talk. So first, I will briefly mention what is natural language processing and why NLP is hard. And then I will introduce my research on question generation, which is the main part of this talk. And I will also briefly introduce my research about ontology creation. And finally, briefly mention an ongoing work about logical reasoning. So let's start from what is natural language processing? So actually, natural language processing is everywhere in our daily lives. For example, there are many products of Google, Google Translate, the search engine, and Bing, Yahoo, Baidu, and many other search engines. And I think a lot of us may have used smart speakers from different companies, such as Amazon Echo, Google Home, and so on. And recently, there are many companies are talking about some concepts like the metaverse and the research about chatbots or virtual characters, or we say avatar. So it includes the Microsoft Xiaoi's, the Xiaoai from the Xiaomi, and Bilibili Yosa and Baidu's Xiaodu, and Mihayo Yoyo, and so on. So basically, for these different chatbots, they have the ability to communicate with people or generate the musics and many other artworks. So basically, this is a kind of a format which integrates the different tasks in natural language processing. And there are many mobile apps which they rely on different natural language processing tasks, includes the social network apps, WeChat, QQ, and Twitter, Facebook, and Google, Weibo, and so on. So we have like different parts in these apps, including the searching, the feed news streams, the analyze of the short text, such as Twitter and microblog, and the analyze of the long documents, like the news media and so on, and also the chatbots for health and so on. So formally speaking, language is a tool of human communication and a carrier of human thinking. There are almost like 2,000 different types of language in use all over the world. And the structures of the different languages vary between them. And the natural language is a human language, which is opposed to constructed language such as C programming language, Python, and so on. And so basically, if we have a machine which can process the input language and output language so that it can communicate with human beings, then the path from the language to the format, which is understandable by the computer, is the process of natural language understanding. And the process of generating the language from its internal representation is the natural language generation. And why NLP is hard? There are many reasons, and we will mainly talk about ambiguity and knowledge here. So for ambiguity, so if we look at this example, so we have a sentence, at last a computer that understands you like your mother. So we can actually understand it in different ways. For example, it can mean that it understands you as well as your mother understands you. Or it means it understands that you like your mother. And or it can also mean it understands you as well as it understands your mother. So basically the different meaning of the sentence corresponds to the different interpretation of the syntactic structure And we also have ambiguity from the semantic level or the acoustic level and so on. Another challenge is about is the knowledge. So basically to understand the language, it's hard to purely interpret the word from the text itself. So to understand a sentence, we need knowledge about different things. So the knowledge about the language itself, knowledge about the word, and knowledge about common sense and so on. So if we look at these two sentences, the first is, I dropped the glass on the floor and it broke. And the second is, I dropped the hammer on the glass and it broke. So what does the it means in each of the sentences? So we know that the first it means the glass and the second is the floor. So we can know that it corresponds to the different part of the sentence because we know the common sense about the physical property of the different objects, but it cannot be captured from the text itself. So state-of-the-art measures about natural processing tasks are mainly based on pre-trained large-scale language models. So start from the success of the BERT model. And we have like a lot of drivers from this base model. We have the Roberta, Elmo, we have the GP2, XLNet, and so on. So basically for these models, they include the pre-training from the large corpus of text and the fine-tuning on different tasks. So basically, a language model is things you use every day. So it's the task of predicting what word comes next. For example, if you input some text in your search engine, then you will have like a lot of candidate queries, which helps us like what you are going to input the next. So this is like predict the next word based on what you have already typed in your cell phone or in your computer. And here we can see some examples, what the current pre-trained language model can do. So for example, this is the AI writer created by, I think it's GPT-3. So if you give the model a start sentence, it can complete it by a whole document. So this article, it looks like an article written by a professional scholar. So it's hard to tell like whether it's a generated text from a machine or it's generated by a human writer. And it's not just written articles. For example, it can also produce like the code for a designer based on your requirement. And it can also even produce the machine learning code based on what you need. And this is also actually a kind of language model. So basically it generates, it's a kind of multi-model pre-trained language model. So based on your text prompt, it can generate the image based on your text description. So you can see if you input like an armchair in the shape of an avocado, you can it can produce this kind of image. And if you input like a storefront that has the word OpenAI written on it, and this generated images also satisfies your requirement. So this is the work from the OpenAI, which is the DALL-E model. So the common paradigm of such kind of pre-trained language model usually consists of two parts. So we have the pre-training part, which is like you pre-train a large-scale language model based on a large corpus. So you just predict the masked part of some sentence. It can be from the left to right, or it can be some missing words in the middle of the sentence. And then after you pre-trained this model using this unlabeled text, you can fine-tune it over some supervised learning tasks. For example, you can supervise it, fine-tune it on question answering task, or part of speeching and so on. So in this process, we still need the training data for the downstream tasks, but it's actually not easy to acquire large scale and high quality training data for different tasks. For example, for question answering, if you need like a large corpus of question answering data set, it actually costs a lot and time and human effort. And also, the current state of the art language model still lack of enough common sense and knowledge. So here shows the example like produced by the GPT-3 model. So if you look at the left part, you cannot tell that it is a chatbot. Actually, it's almost correct. So what is your favorite animal? My favorite animal is a dog. And why? Because dogs are loyal and friendly. So if you look at this dialogue on the left, it's very natural and you cannot tell whether it's a robot or not. But on the right, if you see this example, so if you ask how many eyes does my foot have, and it responds, your foot has two eyes. And how many eyes does a spider have? A spider has 8 eyes. So you can see that even though this response is natural in terms of the grammar structure, but it doesn't satisfy our common sense about these different type of objects, about these animals. So a lacking of enough common sense and knowledge is a serious problem of these language models. So the DIC-ISC pyramid tells that from data to wisdom, we have like more and more high-level information here. So for data in its native form, it is sparse, distributed, and unstructured. So it's chaotic. And when we transformation and organization, so we can transform data into information. And knowledge is connected information. And identify meaningful pieces of information and relate them to each other leads to insight and wisdom. So creating data set actually costs time and money, as we mentioned. So nowadays, there are like many companies which like mainly focus on labeling data for a big company. So for example, the super annotate 20 billion remote tasks and so on. So these companies are like designed for creating training data set for machine learning tasks. And understanding language needs to understanding the world, as we mentioned the example about how to interpret it in these two different sentences. And also perception is not enough. We also need logic and reasoning. So as described in a book that the human brain has like kind of 2 different systems. So for the system 1, it is good at like fast processing and be unconscious. And it can automatically do some everyday decisions, and it's usually error prone. So basically system 1 is mainly focused on perception level intelligence, and it's what the current deep learning systems are good at. And for system 2, it's used for like slow, conscious, and effortful decision making. And it can help us to perform complex decisions, and it's more reliable. And for system 2 part, it is like what we need to further enhance in the current machine learning models. So to summarize about our current part of our current research, we are trying to improve the deep learning models in terms of the data level, information and knowledge level, as well as the wisdom level. So for the data part, we perform automatic data set creation. We want to like reduce the effort of creating large-scale data set, and also improve the learning efficiency of the data. And the second is the text mining and knowledge construction. So we want to construct ontology or knowledge graph from unstructured text. For example, short text like queries, and the long text like web pages or documents. And for wisdom, we want to improve the reasoning ability of machine learning model. So basically, our current research is about learning and reasoning with graphs, so that we can enable the machine to perform more human-like reasoning, and it's like more transferable and robust. So my talk about our research will cover like the data part is about efficiently creating data sets with automatic question generation. And for the knowledge part, we will talk about modeling the world with ontology creation and expansion. And for logic part, I will briefly mention a work about real discovery with reinforced and recurrent relational reasoning. So let's start from the first part, which is about question generation. So here our problem is how to generate question and answer pairs from unlabeled corpus. So here gives an example. So if you have a passage, Tony gave a speech yesterday in New York, and the existing research about question answering is mainly focused on answer-aware question generation. So basically you have a passage and you have an answer. For example, here the answer is Tony, and in your data set, you are supposed to generate a question like, who gave a speech yesterday? So this is called answer-aware question generation because you know the answer as an input. But we have a problem. So if you have an answer, actually you can ask different questions which has the same answer. For example, for this input, you can ask who gave a speech yesterday or who gave a speech in New York and so on. So for these different questions, they all satisfy with this input, passage and answer. But in your data set, you only have the one golden answer. So in this way, if you generated another satisfying question, you won't get a full score based on your data set. So this is called the one-to-many mapping problem because you have the one type of input and actually you can have many different outputs, but in your data set, you only have one output. So we analyze like how human ask questions. So let's say if you have this passage, so you may first select a part of the passage as the answer. For example, we select Tony as the answer part. The second is when you ask a question, you need to like repeat or rephrase some part of the input as your message in your question. So for example, we call it as clue. So here we can use gave a speech yesterday as a clue for the question. And also you will have a style for your question. So here your answer is a human's name, then the style will be who. So you will generate this question. So who gave a speech yesterday? And the answer is Tony, and gave a speech yesterday. What is repeated in this question as a clue, and the style is who. And if you change a part of input, for example, if you replace the clue with gave a speech in New York, and you will have a different question, who gave a speech in New York? So based on this kind, the interpretation about the process of human asking a question, we designed the answer clue style aware question generation, so which is called ACS aware QG. So basically the idea is instead of input the passage and the answer as the input, we want to input more fine-grained inputs with more different types of information so that we can have like a more fine-grained control over the generation process. And also based on more fine-grained inputs, you can actually have almost one type of output so that the one-to-many mapping problem will be reduced to almost one-to-one mapping. Because you have so much input to control your output, the target question it's hard to have like two different kinds of formats. So here, this is the system architecture of our ACS aware QG. So the pink part is about obtaining data set. And the blue part is about sampling the inputs. And the internal part is about the generating the question based on the sampled inputs. And the filter can control the quality. And finally, we output the filtered passage question answers. So this is a paper which introduced the whole system. So next we will introduce each module. So the first module is we didn't have how we can get a training data set for our new task. So in existing question answer data sets, we have the passage, we have the question, and we have the answer. But we didn't have the clue and style defined in our task. So we need to like obtain it automatically instead of ask humans to labeling this task. So first, to get the clue part, we show the phenomena of copy or soft copy. So for example, here we have a passage. Erin is 5 years old. And if you ask a question, how old is Erin? So here, this word old is directly copied into the question. So this is the clue part. But in another question, you have this question like, is Erin an adult? So here, adult is not the same with old, but actually the word old in the passage is the reason why you have this adult in this question. So we call this like highly correlated words in the question. Is a kind of soft copy from the input passage. So based on this principle, which it says that clue is a part of the input passage, which is copy or soft copy to the question, we can get the clue part by this copy mechanism. And we can get style by rows. So basically, for this copy part, you can like enumerate the different n-grams in the passage and different n-grams in the question. Then you calculate the sum score to get the overlapping scores so that you select the phrase which have the maximum length and the maximum similarity with the input passage. So for details, you can look at the paper. And for styles, you can like, we extract the style of the question based on some rules as well as a simple classifier, because it's just like most of the time you can identify the style from the first word of the question. And for some other cases, a simple classifier can like identify the type of the question. So we have different types: the who, what, why, how, either, and other types, and so on. And the second part is sampling the inputs. So here we have the problem of input volume explosion. So basically for sampling inputs, it is that if you have a sentence, we want to sample different types of input to generate a question. So we have the passage P, and we also need to sample the answer part A and the clue part C, and the style S. So we have the input volume explosion problem. So basically it means that if you have a sentence, actually you can sample many different combinations of this answer clue style combination. For example, if you have a sentence which contains only like 10 words, you can actually sample over 1,000 types of ACS combination. So for these tuples, most of the tuples are meaningless. So for example, if you sample answer A as 20, the clue is in, and the style is when. So here we can say that the style doesn't match with the type of the answer, so that you cannot ask a worthy question based on this tuple. So to solve this problem, we propose a sequential sampling mechanism. So basically, we decompose this sampling process by a sequential factorization. So first, we give the passage P, we sample the answer part A, and then given this P and A, we sample the style S, and finally, we sample the clue based on the previously sampled information. And to get like the probability distribution of these three different conditional distributions, we can actually like get these statistics from an existing data set. For example, you can calculate these probabilities based on the scored data set. And finally, to generate questions, we adapted the encoder-decoder sequence-to-sequence model with attention mechanism and copy mechanism. And we also adapted the GPT-2 model to generate our questions. So for the GPT-2, we can incorporate the position of the answer and clue as a position encoding in the input part. And then we can concatenate with the passage, with the position information, and with the style, and then use the output, use the question as the output. So that based on this kind of format, we can fine-tune the GPT-2 language model over our dataset. And finally, we further train a binary classifier to control the quality of the generated question answer pairs. So here, if you have this input passage and you generated this question with an answer, basically it's a textual entailment problem. So it means that if you concatenate the question with the answer, the meaning contained in this QA pair will be entailed with the input passage. So this is a binary classification. So based on our SSQG system, we generated like almost 3 million question answer pairs based on from 10,000 Wikipedia articles. So by a small scale human evaluation, we found that the questions generated by our system, like more than 70% of them is well formed, which means that if you look at the question, it doesn't have like serious syntactic problem. And more than like 65% of the question is relevant instead of some random question which is not relevant to the input passage. And in overall, more than half of them is correct, which means the question doesn't have like important grammatical errors, and the question is relevant, and the answer matches with the question. So on the left, we show an example. So if you have this input passage, you can generate different questions with different answers. So the orange color indicates the style of the question. You have the what and which type. And the blue is the answer of the question. And the green part is a clue from the input passages. So we can see from the same sentence, we can have different combination of keyword pairs. And we evaluated the performance of our question generation system, which is the CS2S via ACS model. We can see that the performance in terms of the blue scores and the rank and meter is much better than the previous baselines. And we have also mentioned another work, which is the CGCQG in this table. It's actually our previous work. So in this work, we didn't like use the clue as an input. Actually, we just predict which part of the passage can be the clue. And actually, we can say that this CGCQG model also outperforms many other baselines, which indicates that even though you didn't fit the clue part as the input, it's also helpful to predict it so that your model like generates the question more like the human process. So in this work about question generation, we generated a lot of data, but the performance of question answering is not improved yet. So basically, we improve our generated data to train a better question answering model. We found that the performance is not as good as training on the original data set. So the reason is there are many aspects of the reason. So for example, your generated question is like homogeneous with the questions in your data set, so that even though you have more training data, your model may be already familiar with this type of questions, and it doesn't need more this type of questions. And also you have like many errors in your data set. So this noise will further like lower your performance. So our next work is about difficulty controllable question generation. So basically in this work, we want to improve or control the reasoning logic and the difficulty level of our questions. So for example, if you given this context, Tom Cruise began acting in the early 1980s and starred in the action film. And for this DIC-QG, which is difficulty controllable question generation, we want to control the output questions difficulty level, the underlying logic, as well as the answer. So we can have different questions. Who starred Top Gun, or who starred the film directed by Tony Scott, or who starred a 1986 action film directed by Tony Scott. You can see that the questions are actually become more and more complex with the same answer. So this is the framework of our difficulty controllable question generation. So the idea is like we first turn the context into a knowledge graph. So it's like a document level knowledge graph. Basically, we extract triplets from the context and connect them. And then we perform step-by-step question generation. So first, we will like sample the reason chain. we will sample a triplet from the graph, and based on it, we will generate an initial question, which is called Q1 in this framework. So the Q1 is like who directed dial M for murder. And then based on this initial question, we will rewrite it into a more complex one. So basically we will sample another reasoning chain, which is related to the part we want to replace. So here, from the Q1 to Q2, we get the who directed the film to which a prefix murder was a modern remarker. So here we show the process. So first, we convert the given raw text into a context graph. And then we sample a reasoning chain and the answer of the generated question from the graph. So here we choose Tom Cruise as the answer node. And we sample this red part. And we have this step-by-step question generation. So first we generate the initial question based on this triplet, the Tom Cruise start Top Gun. So we have this question, who start Top Gun? And next we revise the initial question to a more complex one. So here, Tom Cruise is replaced by the film directed by Tony Scott. So this corresponds to the second chain, triplet. So Tony Scott directed Top Gun. And we can further improve the complexity of the question, which is like introduce more reasoning hops into the question by sampling another related triplets in this knowledge graph. So we can get this Q3, who starred a 1986 action film directed by Tony Scott. So you can see that by gradually increase the complexity, increasing the reasoning hop of this question, you can control the difficulty level and the reasoning logic of the output question. So we also need to construct a dataset for our task. So basically we utilize the hotbot QA, where most of the questions require 2 hops of reasoning, and we'll implement a question decomposer, which can decompose a 2-hop question into 2 sub-questions, sub-question 1 and sub-question 2, based on the spam prediction and the linguistic rules. And finally, we can get a dataset that contains 2-hop questions and the corresponding 1-hop questions. So for example, if you have this QA pair from the hotbot QA, it is a 2-hop reasoning question, and we can get like these 2 sub-question 1 and the sub-answer 1, as well as this sub-question 2 and answer 2. So in this way, we don't need like a human to manually create a dataset for our data, for our task. Instead, we just generate it from an existing multi-hop question answering task. So in this, based on our difficulty controllable question generation, we generated more dataset from the existing hotbot QA, and we can see that if we fit the generated data into the question answering model, so here we train a GPT-based question answering model. We can see that. So we have like 2 different settings for the experiment. For the orange experiments, we use 100% of the original hotbot QA data, and we use another half of our generated data. And in the low resource setting, we have only like 25% of the original hotbot QA, and then we augment it with our generated data. And here we compare with the baseline, which is the question generated by GPT-2 model. We can see that if we increase the dataset by our generated data, no matter whether we have the full dataset or we have only like a partial of the hotbot QA, our generated data can actually increase the performance of the question answering model. And also our performance is keep being better than the baseline GPT-2 model. Our third question is like, how good is the data and the question answer model? So first we can consider this example So what capabilities are needed for ping pong? So a competency assessment is that assessment of someone's capability against the requirements of the job. So we know that for the ping pong player Malone, we call it like the sixth fully equipped player. So basically, he's a very excellent ping pong player who is like very good at different skills. So he has very good power, speed, skill, tee-off, defense, and experience. So and it's also like if you consider about an NLP model, for example, if you consider the capability of a model for question answering, you may ask like what kind of skills is needed for a model to answer different questions. So our question is like what capabilities are needed for question answering. So here we show two questions. So two example questions, question 1 and 2, with different difficulties require different capabilities. So for question 1, like who is the trouble making turtle? And the answer is James. So actually for this question 1, you only need to match the words between the question and the context. Because in the context, you have this sentence, James is a trouble-making turtle. So if you match question 1 with the context, you will easily find the answer is James. And for question 2, where did James go after he went to the grocery store? And the answer is a fast food restaurant. So here it requires more complex capabilities. So it needs you to understand the syntactic matching, the temporal relation between different actions, and the semantic overlap between question and the context. So basically in our work, we define 4 major capability dimensions for understanding text and self-viewing machine reading comprehension tasks, so which are inspired by the computational model of human text comprehension in psychology. So basically we define like 4 types of capabilities: reading words, reading sentences, understanding words, and understanding sentences. So for reading words, it includes like the ability of recognize vocabulary, recognize function words, and so on. And we use the metrics from the different existing works. And for reading sentences, it means the ability to recognize the sentence grammatically and the readability. For understanding words, it means the ability to perform arithmetic operation, logical operation, and so on. So for example, if you compare reading words and understanding words, if the model knows a word is a number, but it cannot like sum up the 2 numbers to get the result of this sum, it means this model can read the words, but it doesn't understand the word because it doesn't know how to operate over these words. And the last is understanding sentences. It consists the ability of like perform linguistic reasoning or factual reasoning and so on. So basically for these different categories of capability, we use existing metrics to calculate a lot of values, and we normalize this value and get the final score for the different capability dimension. And based on the capability measure of a question answer model, we further propose the capability boundary breakthrough curriculum learning. So the model capabilities are passed by the corresponding difficulty sample subset, and the samples around the capability boundary are picked to strengthen the model. So if you look at this pipeline, basically we means that first we have sample pools. So we have these different shapes correspond to the 4 types of different capabilities, and the color, the shadiness of the color indicates the strength of the difficulty. And here we have the hard development set. So basically, for different capability, we have a set of samples which is like have a high difficulty in a dimension and is easier in the other dimensions. So basically, based on this hard development set, we can measure the capability of the model in terms of the 4 dimensions. And then when we select the next batch to train the model, we will select the samples, which is like it has a difficulty around the boundary of its current capability. It means that if you want to efficiently learn your model, you need to like select the samples, which is either not too easy or not too hard for the current model to serve. In this way, you're trying to push the model around the current capability boundary. In this case, you're actually guiding the learning of the model based on your measurement about its capability status. And also the current model's status also can guide your model to generate more appropriate training data. And this is the experiments indicates that actually by training the model with our current the curriculum boundary breakthrough strategy, actually we can improve the learning efficiency because we are selecting more appropriate training data based on the status of the model. And the right figure indicates that the most important part is about the first dimension, which is the capability of understanding sentences. This helps to improve the learning efficiency of the models a lot. This figure shows that during the learning process, all of the four-dimensional capabilities are keep increasing based on our curriculum boundary breakthrough training strategy. Okay, to summarize. So first we generate question answering pairs from unlabeled text. So we use factorizing input information and the sequential sampling as well as the automatic dataset creation to consist our system for this question generation part. And then next, we control the difficulty of the generated question answer pairs by combining the graph representation of the input passage and by sampling the reasoning chain from the passage. And we sequentially increase the reasoning hops of a question to control the difficulty level of the output. And in our third work, we measure the capability of a question answer model. So we define the different data properties or model capabilities. And we propose the capability boundary breakthrough curriculum learning to help the model to learn more efficiently based on the data. Next, I will talk about our research on ontology creation. So here the problem is how to infer the user's interest. So for example, if a user input a query to estimate recognition speech in the search engine. So if a recommender system recommends articles about Résumé, this may cause a problem of inaccurate recommendation because the user may be not interested in Résumé herself. Another phenomenon is the recommender system may recommend other articles about Résumé's recognition speech. However, the user may already have read several news articles about this event. So this causes the problem of autonomous recommendation. And a good recommendation may be articles about Brexit negotiation. To achieve such kind of a performance, we need like two parts. The first is we need to identify that the user interest in a suitable granularity. So we must know that Brexit negotiation is a good user interest. And the second is we need to identify the relationship between user interests. So we need to know that the event Résumé's recognition speech it actually belongs to this topic, Brexit negotiation. So in this way, if we see that the user read some articles about Résumé's recognition speech, we may think, oh, this user may be interested in the topic, Brexit negotiation, so that you can recommend news articles about other events belonging to this topic to this user. So we need to ask, like, what kind of information does people care about? So the first type is events. So we define events as a real-world incident that involved specific persons, organizations, or entities with a certain time or location of occurrence. For example, Theresa May's resignation speech is an event, or Apple launched new iPhone, or iPhone, this year is like iPhone 13. Another type of information people care about are concepts. So we define concepts as a collection of things that share some common attributes. So for example, the Honda Civic, the Honda Electron, we may think these cars are belong to fuel-efficient cars or economic cars. So these are two concepts. Or the Iron Man or Captain America belongs to the concept Marvel heroes or Revengers. So what we did is in our work published in Sequential 2020, so we created a web-scale ontology to represent user interests and document topics. So here we can see the whole architecture of the ontology. So basically we have like different types of nodes in the ontology. It includes the black nodes, which we call category. So they contain like more than 1,000 different predefined categories, includes like the technology, current events, and so on. And then we have the different phrases, which are mined from the user queries and document titles. So which includes the concept phrases, the topic phrases, and event phrases. For example, we have these like pretty cell phones for the elderly, and so on. And we have the different events, topics, cell phone launch, Résumé, Brexit negotiation, and so on. And we have different events. For example, Apple launched new iPhone, and so on. And also we have the entity nodes. So for different entities, it may belong to different concepts. And for the edges in this ontology, the main part is the either relationship, which indicates the an event belongs to a topic, or an entity belongs to a concept. We further define the involved relationship and the correlated relationship. So the involved relationship means like some event, some concept is involved in an event. And for the correlated relationship, it actually links some entity pairs, which are like frequently mentioned together in the input query or documents. So the ontology is created by the system, which is called Giant. So here shows the whole framework of the Giant system. So we have first we have like the users, queries, and documents. So in this way, if you like input different queries, you may click different documents. Then this actually can be represented by a biparty graph. So where the left part is the set queries and the right part are the top click documents. And then we perform like query document clustering so that we can split the big biparty graph into different small query document clusters. Well, in each cluster, you will have like several highly semantically the same queries and highly related documents. Then for each cluster, it is possible that we may extract a phrase from it. It can be a concept, an event, or a topic. And then we have an algorithm to identify the relationship. So if you have like a new phrase, which is a new node in the ontology, you can find a place to insert it into the existing ontology. And finally, based on this ontology graph, you can actually use it to tag the user interest for different users. And you can use it for document tagging, which like you can tag a document by some concept tag or event tag to indicate its main content. It can also be utilized for the query conceptualization. So if you input some like entities in the search engine, you can infer that you're actually interested in some type of concepts or topics. Then actually it can help to generalize your query query into a more broad range of topics. So here, the key research problem is like how to mine the heterogeneous phrase from the queries and titles. So here we show an example. If you have this query, what are the Hayao Miyazaki's animated film? And you have like different documents which are related to this query. And the objective here is like whether we can extract this phrase. Here is a concept, Hayao Miyazaki animated film. And for other phrases, for example, events or topics, the algorithm is the same. So we can analyze the characteristic of the output words. First, they actually show some patterns in the query and the titles. And the second is they actually show up multiple times. And also the named entity or part of the text of these words are useful because most of the output words may be a name, noun-phrase, instead of some stop words and so on. And also, most of the words, they are continuous chunk in the query or title. And sometimes you may have like one or several stop words between them. But most of the times, they're actually a continuous phrase in the original query and title. And finally, even though these words may like shuffle a little bit in different places of the query or titles, the syntactic dependency of them between the different words in the concept phrase or event phrase, usually the syntactic dependency won't change. So based on this analysis, we want to like try to show these features more obvious. So basically, we turn the queries and titles into a query title interaction graph. So here we show the graph constructed from the previous example. So basically, we have for each query and title, we add a virtual node, start of sentence SOS, end of sentence EOS, and we have these different word nodes. Then for all the queries and titles, we merge them. So each node represents a unique word in a query or a title. If two words are adjacent to each other, we have like a sequential urge between them. Otherwise, we check whether the two words have any syntactic dependency between them. If yes, we add the syntactic dependency between the two words. And finally, for each type of urge, we also add the inverse urge between them. So basically, the patterns in the sequential text tends to the graph structured pattern. And the feature that they may show up multiple times turn into the node feature. And the word text also can be represented by the node feature. And the continuous chunk are actually indicated by the sequential urges between different word nodes. And the syntactic dependency was like captured by the syntactic urge between different words. So to extract a phrase between from this graph, first we need to classify whether a word is belong to the output phrase. So here the Hayao Miyazaki anime film. So these three words belongs to the output phrase. So here is actually a node classification problem. So we trained a relational graph convolution network to perform this task. And after that, we need to arrange the different words into the output phrase. So we need to order them. So basically, we consider it as a asymmetric traveling salesman problem. So what we want to find the shortest path from the start of sentence to the end of sentence. And this path will go through each of the output words for one time and connect them. And this path has the shortest length among every possible passes. And this problem can be solved by existing algorithm. So we have talked about how to mine different phrases from the query and titles. Basically, it is a node in the taxonomy. The next problem is how to add a new term into the taxonomy. So let's say if you extracted a new concept, you need to find the most suitable place in the existing taxonomy or ontology. to insert it. So this work we published in the Web Conference 2021, solves this problem by so here shows the whole framework of our model. So we won't go to more details, but I will briefly describe it. So basically, the previous research work, they mainly compare the input query node and candidate answer node, candidate father node. So basically, they are classifying what the input query queue has the parent-child relationship, the user relationship between this queue and answer node, the anchor node A. But in our work, we infer like whether this input query belongs to like this path. So we not only compare it with the parent node, we also compare it with the ancestors as well as the candidate node's children. So if this query node is good to insert as a child of the parent A, then it should be like very coherent with its children, so because they are siblings. And also it should be like coherent with the ancestors of this parent node. So basically we compare the relevance between the input query node and all these ancestors and the child. We call this structure as the ego tree. And also the name of these nodes are not only the names, so we expand the description of each node by the definition in the word node. So here shows the application scenario of our like giant system. So here, this is like some fixed news streams in the browser application. So here shows a document. So the title is like cities cars with less than 100 km fuel consumption and up to 1,000 kilometer recharge milli. And we can tag this concept, low fuel consumption cars, to this document, which indicates that this document is actually talking about some low fuel consumption cars. But we can see that this concept is never shown in the title, or it also not mentioned in the document with the exact wording. So in this case, we can actually describe the main content of the document by such kind of short text. So for logical reasoning, so here is our ongoing work. So basically, we want to enable a model to perform to reasoning over graphs. So for example, here shows an so let's say we have this graph 1 and graph 2. So we hope that our model can learn from some simple inputs to learn some simple rows from the training data. And then it can be able to combine these learned rows and reason about more complex examples. So let's say from the training graph 1, we can learn a row. If X is the mother of Z and Z is the sister of Y, and we can infer that X is the mother of Y. And from the training graph 2, we can learn another row. If X is the mother of Z and Z is the father of Y, we can learn that X is the grandma of Y. Then we hope that a model can predict on figure 3 using the aforementioned 2 rows. So we proposed a reasoning mechanism which is called R5, which means like recurrent relational reasoning for row extraction. So basically, our idea is like if you have like graph input data and we want to reason about the relationship between two candidate nodes, let's say X and Y, and actually it's like playing a Go. So you can extract different passes between X and Y, and then what we need to do is like whether we can go through one of the paths and merge all of this relationship to the final relations based on some row compositional rows, relation compositional rows. By talking about these rows, it's like the relation 1 with relation 2 can be merged into relation 3, just like just like if you combine the mother relation with the sister relation, and you get the mother relation, and if you combine the mother and the father relation, you can get the grandma relation. So if you go through a path, it's like during each step, you are sampling an action. Well, each action is like whether you can merge relation 1 and relation 2 in output relation 3. And by iterate over this process, and finally, one of the paths will be merged into the final output relation. And we actually learn some reinforcement learning-based agent to perform this reasoning process. And yeah, so this work is still under submission. So currently, we don't have like more details about it. So basically, it looks like the Go algorithm. So it's just based on the reinforcement learning, and we design a dynamic row memory to store all the actions we have utilized during this process. And we have like a scoring mechanism to assign scores to the different rules we have tried, which is also the different actions during this process. And finally, we will keep the growth with a score above a threshold. And thanks. Any questions?
Okay, thank you very much, Professor Bang. So yeah, it's time for questions. Thank you for the presentation. So I have here some question asked by first Stephen Harnad. Professor Harnad made a comment in the chat.
Yeah, I'm looking at
about correction of two phrases.
So the question, it broke means the same in both sentences. The only difference is that you can see I dropped the hammer on the glass and the hammer broke the glass, but not I dropped the glass and the glass broke the glass. Because I dropped the glass on the floor and the glass broke the glass. Yeah, I think this is a comment.
Yeah, it's comment, it's not a question,
yeah.
Right?
Okay.
Yeah. The next question is from Pierre Vadnet. He said, in New York yesterday implies a sound basis about time space. What is it coming from? Where is it coming from?
So in New York yesterday implies sound basis. Yeah, so in New York, it's actually, if you look at the example, it is also a part of the input passage. So let me go to the slides. Yeah, so here's the passage like Tony gave a speech yesterday in New York. So basically you have like two conditions defines the speech. So it happens yesterday, it happens in New York. So either one of the input message can be the clue part in the question. So that's why we can select yesterday as a clue, or you can select the in New York as a clue.
Okay, thanks. So the next question is from Albarasa. Could this ontology be structure learned as opposed to imposed? Should the relationships be qualified?
Yeah, so basically in this ontology, the main relationship is still the ether relationship, like most of the ontologies. And we actually, the manually designed part is the categories. So we manually designed like a top level categories, which covers the domains we are interested in. And all the others, so we extract the phrases from the query and titles, and we identify entities from documents, and we identify the relationships automatically instead of like with too many human designs here.
Okay. Okay, thank you. So is there any question from the audience, people, students? Okay, Pierre Vatny.
Yes, if I can come back to the question about in New York yesterday. In fact, somewhere the system knows that space-time exists. How did you give that to the system? Somewhere you say that New York answered the question of where, and yesterday the question of when, but how does the system know that when and where exist? How did it learn that? Or did you simply?
So in the setting of the question generation or question answering works, tasks, so the passage is like fit as a part of the input. So for example, if you are serving the question answering task, you have this passage as the input, and you ask the question, so like who gave a speech yesterday? And the system needs to reason about this question by combining this question with the input passage. Tony gave a speech yesterday in New York, and then give the answer. So the information source is from the passage itself.
Maybe the named entity is a clue to generate this question. The fact that there is New York, so we can generate the question with where or who. We can generate it with Tony.
Yeah, so for the question generation, so the answer, the passage, and the clue. So basically the passage, answer, clue, and style, all these four parts are our input. So let's say if you have this answer and this clue and this style, then the question can be who gave us speech yesterday. Because you have defined that gave us speech yesterday is a clue part, then this part shall be like copied or rephrased into the question part.
Yes, but you're talking about understanding. So somehow you assume that the system understands that gave a speech implies that it was done somewhere at some point in time. But nowhere in there, I agree that yesterday means some point in time and New York's some place on earth. But I know that New York is somewhere in the world and yesterday is somewhere in time. But the system doesn't know that. So it doesn't really understand that it can make the question yesterday. It knows that it can make a question about yesterday or about New York only because you say that these type of questions exist. So you're somewhere, you are building behind the system a basic ontology, at least about space-time and so many other things.
I agree. Actually, as mentioned by Professor Fatiha, so the named entity recognition, named entity tag or the part of speech tag can help to like give the information about the different inputs. So we know that the New York is a place, then it can ask like where, and if the answer is Tony, which is a human being, then the question will be about who. So when you talk about like give a speech, needs to understand it happened in somewhere and at some time. So basically, this is just learned through the text generation part of the model. So I don't think like the current model can actually understanding the scenario semantically with like a word model. So it basically lacks the pattern between the inputs and the outputs.
Yeah, so research most of the time on question generation relies on the 5W and the 1H, how. So this generates answers, very basic answers for information gathering and corpus question answering corpora construction. So how about complex questions with complex answers? In addition to the 5W, and the one page.
Yeah, so currently our complex questions are mainly about the multi-hop question. So if we want to like a more complex one, which requires more complex reasoning. So basically our hypothesis is that we can like try to formulate the input into a structured way, and we can like summarize the different parts of the input as like a hyper edge or hypernode in your representation. So for example, if you have a document with talking about a complex event, and you can ask like why something happens, and this actually needs you to reason over the complex details in the document. This actually like you're asking a higher level relation between a subpart of the document and another subpart of the document. So in this way, instead of asking questions about a very specific information like who, Tony, or where in New York, you need to understand the document in a more broad range, and you need to reason the relationship instead of only in the syntax level or in a short span. You need to actually try to link the message between a part of the document and another part of the document with some like causal relationship and so on. So currently I saw some research about introducing like causality into the NLP models. I think this can be a very good research direction to improve the model's ability to understand complex relationship between the in the text and ask more complex logical questions.
Okay, thank you. So Professor Jean-Guy Meunier has a question.
Well, thank you very much for this highly sophisticated presentation. I did understand all the parts, but what seems important for me is that your model doesn't process natural language just like having occurrences of words or bags of words. You throw on the sentences a certain symbolic structure. Am I understanding you? Which are debatable, but the important hypothesis that I understand is that if you want to process a natural language sentence, you cannot just have bags of words. You must project or map on them a certain structure. The difficulty, or it's a difficulty, but it's interesting, and it's related to Fathia's question, is that this projection or the mapping of the structure or a certain symbolic logic structure on it seems to be justified by your using common knowledge, common knowledge about the world. Yeah. New York is a city, and New York is a time. This is common knowledge, but there are certain texts that are a little bit more sophisticated. New York can be something else than just a place. It can be what I said, a symbolic image or phantasms of somebody. Compare New York to Paris. It's not comparing just the roads, it's comparing something cultural, something. And do you think that your model would upgrade or upgrow to more sophisticated and complex understanding of what is a city or a time, place, because that's clear. But often your whole model is related to pushing the symbolic structures on these sentences because you have two or three types of questions: who, where, when. And many texts, at least that type of work I'm trying to do, is it's a little bit more sophisticated than does New York have streets and does New York as just a time. does your system, or have you thought of these problems? How do you upgrade to these higher levels? For instance, in medicine, would you trust your system to answering a diagnostic about something? Because there you're going a little higher. If you go in a psychiatric text, it's not that easy.
Yeah, very good question. Thank you. Yeah, so basically here, I think the core philosophy problem is like, how do you define semantic? How do you define the meaning of a word or a text? So here, if you like use the part of speech or the named entity tag as like auxiliary information or the knowledge about New York or about the time, then we are like using a shallow level syntactic information. So to further like enhance our document, enhance our model to more concretely understanding the sentence, what I think is that actually we need to merge the different common sense or knowledge about different things in a text in a better way. So let's say you can actually, a hypothesis is that we can understand a word by how it is related to other words, or how it's related to other attributes, or how it was used in different contexts. So if you define like a word as a node in a complex graph, and the different text as its attribute, and its occurrence with other words as the interaction between them, and also its syntactic dependency between one word with another word. So we can actually like modeling the context graph structure of a word or a piece of text, and then to better understand a word or a sentence, we can incorporate the different knowledge or different common sense into the graph representation of each word or the whole piece of text. Then based on the modeling of like a rich graph representation of a large corpus of text, we know that like the things like similar to New York or other city names, it is a city which is actually a location, and we can ask questions about where for it. And if we want to understand it in a like more higher level, it's like we're trying to extract graph patterns from the structured representation of text. So yeah, so basically my future research objective is like how we can model the different text into a more sophisticated graph representation, and how we can incorporate or inject the knowledge or different common sense and so on into the modeling of the pure text, so that we can understand the text based on the interaction between different words with different urges, with different attributes. It's like a social network of different text pieces.
May I continue, Fetia?
Yeah, bien sûr.
Do I understand you as that there in the model there's a learning of new information about the cities or the entities? It's not just world knowledge, it's also learning from other text information that will be added in the ontology.
The current model only uses the tag information, but we can actually further enhance it by external knowledge.
Okay, that's very interesting. Thank you very much.
Okay.
Thank you.
Pierre has another question.
In fact, the question is really about semantic. And if you add a passage, or if you use as your passage in your slide there, the famous sentence from Chomsky, colorless green ideas sleep furiously. I'm sure that your system could generate 5-6 questions about the passage, and they would all be properly phrased and everything, but it means that the system did not understand anything. If you try to understand the sentence any human will say, well, it doesn't make much sense, but it's perfectly right at the symbolic level. And this is the problem everywhere. That's the problem that we are trying to solve in artificial intelligence. When do you think it would be possible to get something in that direction? And in fact, you're using the word understanding, but understanding a passage goes further than parsing the words in the passage. It goes to getting what is under or underlying behind this passage.
Yes. Yeah. So let's go to this slide. So basically, my current research is focused on different parts of the data knowledge or logical reasoning. So it's still so to reach what we want the machines to really understand a text, I think we need to integrate the knowledge, the original data, and the reasoning capability very well. So it's like we are still in the initial stage of how to modeling the representation form of the data. So from the original sequential form into also the syntactic level structure, whether we can to extract more high level relationship, more high level structures from the raw text. And also whether we can incorporate, merge the external knowledge to enhance the representation of the text. And based on a more comprehensive representation of the input data, how we can extract the information of different level from the text, and how we can reason about the different pieces of it to answer complex questions. So what I'm aiming for in the future is to further improve the representation form of different data or information or knowledge. And based on a more comprehensive way representation, we want to further improve the reasoning ability of a model to understand the different parts of the text. For example, whether we can identify more high-level causal structure from the text, and whether we can answer more complex questions such as why, and so that we can learn the logic in the text instead of only the pure syntactic structure.
And about this question that you generated, did you make an error analysis to see the errors behind, if there are some errors behind these generated questions?
Yeah. So we have, for example, we have some grammatical errors, and also we have some kind of type mismatching. So we don't have a very concrete percentage about different type of errors.
Okay. There is a question from Simon Ouellet. So do you want to ask it, Simon, or I read it?
Sure, I can ask it, yeah. So it's related to the current questions, but it's a different phrasing of it. So do you think it's possible to reach human level natural language understanding without using grounded language learning? So having an embodied intelligence that interacts with the real world?
Yeah. Actually, this is also my current research interest, how we can understand the text through interaction with the environment. For example, when a baby learns different concepts, the humans are teaching it to show it this is an apple, and it can eat the food. You can eat it. You will taste this fruit. So what I think is that basically we can interact with the different parts of the environment to get feedbacks from it. And the language itself can also be a kind of reward, so that it can help you to enhance the representation of different concepts in the model. For example, if you say something is an apple, and you actually looked at its figure and it will help you to improve the representation of it itself. And also it can help you to identify the relationship between apple and other concepts, for example, the fruit or food or living and so on. So how we can like get different rewards from the interaction, and how we can get rewards from the input text or the language itself is something deserves to research in the future, I think.
Is there any other question? So I have two small questions. So about the common sense that is very important to reach the human performance. So did you think to expand or to generate a common sense ontology or expand an existing one like CYC, which focus on implicit knowledge by generating questions and having answers?
Currently, I don't have a research project on like generating the implicit knowledge or common sense knowledge. So we have, we may have like some research project about like how to generate ontologies in different domain, specific domain. For example, there are many companies in Quebec with like the National Bank or some medical companies. So they want to generate ontology from the bank documents or from medical literature or scientific documents. So for the ontology creation, it's like how we can develop a more general model which can be quickly adapted to different in-domains with the specific in-domain knowledge. I think this is a very important program, so that we don't need to like create a specific model for each domain. Instead, we have like a central model, and we can be quickly adapted to different domains. And also we can combine the power of different data in different domains so that we can utilize the data set from all the different specific domains.
Okay, a second question is about biases. So we know that, I think you used Wikipedia for your evaluations on question generation. So yeah. If, for example, we apply this approach on another corpus, and we know that corpora are biased, so what do you think about the generated questions?
Actually, I haven't taken this into account yet.
Okay. Okay, so thank you very much, Professor Bang. So if there is no questions, so I wish a very nice day to everyone, and thank you again very much.